All right, welcome to this deep dive. Today we're looking at a really interesting paper called ReTool, Reinforcement Learning for Strategic Tool Use in LLMs. It's from the team at ByteDance Seed.
Yeah, this one tackles a pretty big challenge, right? Getting LLMs to handle complex reasoning, especially math problems where, just text isn't always enough. Things like the AIME Olympiad problems are notoriously tough for AI.
Exactly. And ReTool's core idea is, well, pretty neat. They're using reinforcement learning, RL, to teach the language model when it should use tools like a code interpreter, and crucially, how to use it right in the middle of its thinking process.
Right, so it's not just about generating code at the end. It's about weaving code execution directly into the reasoning steps. Real-time feedback from running the code.
And this leads to some pretty impressive jumps in performance, especially on those hard math benchmarks we mentioned. So if you're an AI researcher, ML engineer, anyone really interested in pushing what LLMs can do in problem solving,
then this paper is definitely relevant. It's about making these models smarter in a very practical way, integrating tools strategically.
So that's our mission for this deep dive. Unpack how ReTool works, look at the results, and see what makes it so effective.
Let's do it. The authors, Jiazhan Feng and the team, really lay out a compelling case. We know even advanced LLMs can plateau on tasks needing structured steps, like geometry or precise calculations.
Yeah, that's where code interpreters usually shine, but integrating them smoothly is the trick.
Exactly. And ReTool aims to bridge that gap.
Okay, so digging in, the paper highlights a couple of key features. The first one is dynamic interleaving. What does that actually mean in practice?
Well, think of it like the LLMs having this internal monologue, right? Cool. And part of that monologue is actually running snippets of code and seeing the result immediately.
Ah, okay. So it's not like think first, then code later.
No, exactly. It might be reasoning in natural language, then think, okay, I need to calculate this precise value, generate the code, run it in a safe sandbox.
Gets the number back.
Gets the number or maybe an error message back, and then weaves that result straight into the next step of its reasoning. It's this seamless back and forth.
That seems powerful. It's making the tool part of the thought process itself.
Precisely. It's deeply integrated.
Okay, and the second big idea is the automated RL paradigm. How does the model learn when to do this interleaving without someone telling it?
Yeah, this is the clever part, I think. It uses reinforcement learning, but the reward signal is super simple. It's just based on the final outcome.
The final answer to the math problem.
Exactly. Did it get the right answer? Yes. Positive reward, like +1. Wrong answer. Negative reward, -1. That's basically it.
So it's not getting rewarded for using the code interpreter correctly necessarily, just for getting the final problem right.
Right. And by focusing only on that final outcome, the model is sort of forced to explore. It tries different ways of mixing reasoning and code, and over time it learns which strategies actually lead to that positive reward.
Huh. So it discovers the best ways to use the tool on its own without explicit instructions on how or when to use it for specific steps.
Exactly. It's learning the optimal strategy through, trial and error, guided by that simple outcome feedback.
Okay, that makes sense. So how did they actually train this? The paper talks about a two-phase framework. First, there's this cold start data generation. What's that about?
So the cold start phase is basically about giving the model a leg up. You need to show it some examples of how using code can be helpful before you just throw it into the RL deep end, right?
Right, giving it a starting point.
Yeah. So they generated a synthetic data set. They took existing math problems and their solutions and essentially went through and replaced parts of the textual reasoning with equivalent code snippets and the actual output that code would produce.
Ah, so they're creating examples like, instead of explaining this calculation, here's the code and here's the result.
Precisely. They used structured prompts to help automate this transformation. And crucially, they had a pretty careful verification process.
To make sure the examples were good.
Yeah, 2 stages. First, checking the format, making sure the code tags and interpreter tags were all correct so the model could parse it. Second, and more importantly, checking that the final answer in these synthetic examples was actually correct.
Okay, so you're feeding it good examples of code-augmented reasoning that work.
Exactly. It provides that initial foundation, showing the model, hey, using code like this can lead to the right answer. They detail the prompt for this in the paper. It's quite involved.
Got it. So that's the cold start. Then comes the main event, the reinforcement learning training. How does that build on the cold start data?
Okay, so now the model, which has seen these examples, starts interacting with a live code sandbox. It generates its reasoning trace, mixing natural language and code snippets wrapped in these special code tags.
And when the system sees those tags,
It sends the code inside to the sandbox, executes it, and then gets the result back, whether it's the actual output or, importantly, an error message if the code failed.
errors too. That seems useful.
Definitely. That feedback, the output or the error, gets wrapped in interpreter tags and fed right back into the model's ongoing reasoning process. So it creates this loop. Reason, code, execute, get feedback, reason some more.
And the only thing guiding this whole learning process is still just that final answer correctness. The +1 or -1 reward.
That's the core idea. They explicitly mention wanting to avoid reward hacking.
Right, where the model finds weird ways to get reward points without actually solving the problem better.
Exactly. By keeping the rewards simple and tied directly to the ultimate goal, getting the math problem right, they let the model discover genuinely useful strategies for integrating the tool.
Makes sense. Focus on the outcome. Now, the results they show, especially on the AIME benchmark, they seem pretty significant.
Oh, absolutely. AIME is a tough benchmark, and the results are compelling. Using a 32 billion parameter model, ReTool hit 67% accuracy on the AIME 2024 set.
Okay, 67%. How does that compare?
Well, the key comparison is against a baseline, using the same model, but trained with RL, without the tool integration, just text-based reasoning. That baseline only reached 40% accuracy.
Wow. Okay, so 40% versus 67%. That's a big jump.
It is. And what's more, ReTool got there much faster. It took only about 400 training steps for ReTool versus over 1,000 steps for the text-based baseline to reach its plateau. So better accuracy and more efficient training.
That efficiency point is really interesting, and it didn't just beat its own baseline, right? It outperformed other models, too.
Yeah, in further tests, they pushed ReTool 32B even higher, reaching 72.5% accuracy. And they compared it against other strong models, including OpenAI's O1 Preview, which had outperformed quite substantially by almost 28 percentage points according to their table.
Okay, so it's setting a pretty high bar for this kind of mathematical reasoning task.
It really seems to be. It strongly suggests that this RL approach for strategic tool use is very effective for these complex problems.
And what about that cold start data? How much did that initial phase contribute on its own?
That's also quite telling. The model trained only on the cold start data, with no RL fine-tuning afterwards, already achieved around 40.9% accuracy.
So just seeing those examples got it performing roughly as well as the text-only RL baseline.
Pretty much. And way better than the base model without any fine-tuning at all, which was down around 26-27%. It really shows the value of that initial supervised phase in teaching the model the basics of tool use.
Fascinating. Okay, beyond the headline accuracy numbers, the paper goes into analyzing how the model's behavior changed during RL training. What do they find there?
This is where you really see the learning happening. They tracked several metrics related to how the model used the code interpreter over the course of training. For instance, the length of the model's answers.
Okay, what happened there?
Initially, the length dropped sharply, presumably because it was replacing long text calculations with shorter code. Then it crept up a bit, maybe as it learned more complex code strategies. But overall, the final responses were about 40% shorter than before RL.
So more concise reasoning, basically, getting more done with fewer tokens.
Exactly. Better token efficiency. And then there's the frequency of code use.
Did it use code more often?
Definitely. The code ratio, the percentage of responses containing code, just climbed steadily throughout training. It ended up near 98%, meaning almost every single response involved using the code tool by the end.
Wow, so it really learned to rely on it.
It did. And not just using it more, but using it more extensively. The number of lines of code per response also increased significantly, about 5-fold, suggesting it was writing more complex code.
And was this code actually working?
That's the crucial part. The total count of correct code snippets generated on the test set also went way up. And they looked at the code pass rate, whether the code ran without errors.
Right. What did that show?
What's really interesting is that for responses that ended up with the correct final answer, the code pass rate stayed super high, near 100%. But for responses that got the final answer wrong, the code pass rate tended to be lower and actually decreased during training.
Huh. So generating executable code seems tightly linked to actually solving the problem correctly.
It really suggests that. If the tool use itself is flawed, the code has errors, it's much harder to get to the right answer.
Makes sense. Did it also learn when in the reasoning process to use the code?
Yes, that changed too. Over time, the model started invoking the code interpreter earlier in its reasoning sequence.
Instead of just using it for the final calculation.
Exactly. It suggests the model learn to identify points where a computation would be helpful earlier on, integrating it more proactively into the overall strategy.
Now, you mentioned something earlier that sounded amazing, this emergent self-correction ability.
Yeah, this was, I think, one of the most surprising findings in the paper.
Yeah.
They found that the model, even though it wasn't explicitly trained to debug code, started correcting its own code when the interpreter sent back an error message.
Seriously, how did that look?
They show an example where the model generates code, but forgets to define a function it tries to use. The interpreter sends back a name error. And the model's next step isn't just to fail, it's to say something like, oops, functions need to be defined, let's fix that.
And then it rewrites the code correctly.
And then it generates the corrected code, including the missing function definition, and tries again.
That's incredible. It's like it understands the error message and knows how to react. That feels like a step towards meta reasoning, doesn't it?
It really does. It suggests the model isn't just blindly executing steps, it's developing some level of understanding about the execution process itself and how to recover from failures. A kind of metacognitive skill emerging from the RL process.
Wild. Okay, what about what it used the code for? Did the types of tasks evolve?
Yes, they analyzed the purpose of the code snippets using text classification. Before RL training, the code was mostly used for, basic calculations or just verifying steps, pretty simple stuff.
And after RL?
After RL, the purposes became much more diverse. The analysis showed code be used for things like optimization tasks, geometric analysis, simulating processes much more complex, problem-solving strategies.
So it learned to apply the tool in more sophisticated ways.
Exactly.
Yeah.
The researchers suggest this reflects an improved ability to adaptively select the right kind of computation for the specific subproblem it's facing at any moment. Better tool selection leading to better generalization.
The paper also had that nice comparison, didn't it? Showing a problem solved with just text versus with ReTool's code integration.
Yeah, that was really illustrative. They used a divisibility problem involving a 4-digit number. The purely text-based reasoning was quite convoluted. Lots of manual modular arithmetic, easy places to make mistakes.
I can imagine.
Whereas the ReTool approach after RL training was much cleaner. It quickly identified the need for calculation, generated code to handle the modular arithmetic, and then used code to iterate through possibilities efficiently.
So the code takes care of the heavy lifting computationally.
Exactly. It offloads that complex, error-prone calculation, letting the LLM focus its attention on the higher-level strategy and logic of the problem. It really shows the synergy.
Definitely highlights the power. Okay, let's briefly touch on some of the underlying mechanics. They mentioned using the PPO algorithm for the RL part.
Right, proximal policy optimization, PPO. It's a fairly standard and robust RL algorithm. The key here is that the policy it's learning is the policy for generating these hybrid reasoning traces, deciding moment by moment whether to output text or a code block.
And it's optimizing this policy based on that simple +1,1 reward signal we talked about.
Correct. The PPO objective function guides the updates to the model's parameters to maximize the expected reward, which ultimately means maximizing the probability of getting the final answer right by effectively using the code tool.
And the process of generating these trajectories and getting the feedback, the rollout process, involves that constant interaction with the code sandbox.
Yes, the model generates text, sees a code tag, sends the code off, gets an interpreter response back, result or error, incorporates that, continues generating, and so on until it produces a final answer. That whole sequence is one rollout.
And they had some specific techniques to make this training work well, right? Like interpreter feedback masking. What was that for?
Yeah. That's about training stability. When they calculate the loss to update the model, they basically ignore the tokens inside the interpreter tags.
Why do that?
Because those tokens come from an external source, the code execution, not the model itself. Including them directly in the loss calculation could potentially mess with the model's internal language learning process. Masking them out helps ensure the model focuses on learning the reasoning and when to call the tool, rather than getting confused by the tool's output during the update step.
Okay, that's a subtle but important detail. And what about managing the compute cost? Running code constantly sounds intensive. They mentioned KV cache reuse.
Exactly. Generating text with LLMs involves caching these large key value states. Instead of recomputing everything after the interpreter feedback comes back, they save the KV cache state before sending the code out. Then when the feedback arrives, they only compute the cache for that small feedback part and append it.
Avoiding recalculating the cache for the whole preceding text.
Precisely. It significantly cuts down on the memory and computation needed for each step where code is executed, making the whole RL rollout process much more efficient.
Clever optimization. And finally, that asynchronous code sandbox sounds key to making this practical at scale.
Absolutely. You can't have the entire training process grind to a halt, waiting for one slow piece of code to run. They designed it so there's a pool of worker processes ready to execute code snippets in parallel.
So requests go out, workers grab them, run the code, send results back independently.
Yeah, it allows for much higher throughput. Faster code finishes quickly, slower code doesn't block everything else. It's essential for making RL training with this kind of real-time tool interaction feasible.
Okay, great. So bringing it all together for our listeners, the researchers and engineers tuning in, what are the main takeaways from ReTool?
I think the core message is really about the power of RL for teaching LLM strategic tool use. It's not just giving them access to tools, but enabling them to learn autonomously when and how to best deploy those tools within their reasoning.
And this dynamic interleaving of language and real-time code execution seems key.
Absolutely. That, combined with a simple outcome-based reward, leads to really significant gains in complex domains like math, as shown by the AIME results. And importantly, it seems to be more training efficient too.
It definitely feels like a promising direction for making LLMs more capable problem solvers. Was there one finding that particularly jumped out at you?
For me, it has to be that emergent code self-correction. The fact that the model started debugging its own code based on interpreter feedback without being explicitly trained for it. That's just fascinating.
Yeah, it really hints at deeper learning, maybe even a primitive form of metacognition, like you said.
Exactly. It suggests these models might be capable of developing more sophisticated autonomous problem-solving skills than we initially thought.
So, looking beyond this paper, what are the broader implications? Where might this approach lead?
Well, if this outcome-driven RL works so well for integrating code interpreters for math, it seems likely it could work for other tools and other domains too.
Like what?
Think about scientific discovery using simulation tools, or planning tasks using databases, or even software development using static analysis tools. Any domain needing structured reasoning combined with external computation or information retrieval could potentially benefit.
So it's a step towards more powerful, hybrid neuro-symbolic systems.
I think so. Systems that combine the pattern-matching strengths of neural networks with the precision and reliability of symbolic tools, and learn how to blend them effectively based on task outcomes. The continuous evolution of AI reasoning seems tightly linked to this kind of intelligent tool use.
For listeners who want to dig deeper into ReTool specifically,
Definitely check out the project page. It's retool-rl.github.io. You'll find the paper there, likely code and other resources too. It's worth a read.
great. And maybe a final thought for everyone listening. ReTool focused on code interpreters for math. What other kinds of reasoning tasks out there could really leap forward if LLMs could learn to strategically use the right external tool, driven purely by whether it helps achieve the final goal? What other tools could be integrated?
That's the big question, isn't it? Lots of possibilities there.
Indeed. Well, thanks for unpacking ReTool with us today. A really insightful paper.
My pleasure. It was fascinating stuff.
And thanks to everyone for tuning in to this deep dive. We'll catch you on the next one.